So first of all, let me introduce myself. My name is Wenming. I'm a technical evangelist working for a department called Developer Platform Evangelism. So we're the organization that are customer-facing. We take you through software design reviews and other type of events that we hold right here in the Building 20. In fact, this building is owned by our organization. So first of all, how many of you actually do HPC? Any show of hands? Looks like half of you do HPC. And how many of you planning to use Azure as something you would use? Wow, even more people. Thank you. So my background is computational physics as well as computer science. So I have quite a few years of experience on both topics. And here today I'd like to show you a few examples how you can utilize Azure without very much programming at all to be able to do whatever you need to do. And the first thing I would like to show you is actually this little device. So most of you probably recognize this is in the back of a computer. So the focus is on this part. So how many of you recognize what kind of connector that is? Nobody? And everybody has been doing HPC? Ah, one person. Woohoo! So that little connector is the essence of high-performance computing. What that means is that you have a connector that connects all your nodes at 20 gigabps. It's 20 times the speed of an Ethernet. And the latency on that particular connector is 1 or 2 microseconds. And for the newer versions, it might be even less than 1 microsecond. What that means, you can shovel lots of data very quickly between the nodes. So this is what high-performance computing is all about. In this particular instance, I have a Cray CX1, which is a box about this big, sitting in the data center here in Building 20. I actually have 3 of them, 2 of them not quite working, and I'll explain why. We ran out of power. Some of them have other issues. So that's why you want to work with Azure, because if you have a machine that is broken, you'll be sitting on it for a few months. So Azure used to simply start a few new instances. So the essence of HPC is, once again, low latency and high bandwidth. So for you to shovel a DVD across the network takes you only 1 second on these high bandwidth, low latency networks. But on Azure, we don't have that, and I'll show you how you should still be able to handle a lot of your computing without having that type of specialized hardware. Okay, now an introduction of our group. Technical Computing Group is actually an organization with 200 or 300 people by now. So we mainly focus on HPC as well as the development tools that's behind high-performance computing. So for example, Visual Studio, Excel, and now Windows Azure. And the 3 stands for client, cluster, and the cloud. Basically allowing you to be able to compute on the cluster and the client and the cloud. So here's our session objective. There's only really one for you to understand application scenarios for Windows HPC SP1. Basically allowing you to burst your computation onto the cloud without writing very much programming. And the agendas are live before SP1. So many of you already have your Azure hours. And how do you do compute with Azure itself? And I'll show you an example of a real HPC application on my cluster as well, which is a CFD simulation. And finally, we look at how the on-premise bursting to Azure scenario works. And there are several interesting demos that I want to show you. One is to use the SOA or WCF calls. WCF stands for Windows Communications Foundation. essentially allowing you to farm out WCF calls. And then there's parametric sweep applications, and a lot of people use that scenario for design optimization, where you're running hundreds and hundreds of the application against a set of data that varies in parameter. And finally, MPI, and a look at the what is to come. Basically, yeah, you would be able to run MPI applications on Azure for the next release of our product. So does that make sense so far? Most of you probably understand what MPI is, right? So MPI stands for Message Passing Library. It's a traditional library that has been evolved over about 30 years by now for people to be able to communicate between machines, essentially created for low latency, high bandwidth applications. So if you're doing a matrix solve, that is what that protocol is designed for. So I'm adding a little bit of HPC knowledge in here because this deck particularly assumes that you have some HPC background. So essentially what people have been doing with HPC in the last 30 years is solving linear equations. We have this giant matrix that people are trying to solve. So there's linear equations, nonlinear equations, and then there's PDEs, or partial differential equations. So all of these essentially depend on linear solvers to be able to do these kind of computation. So linear solvers being done in parallel, that is where you need the high bandwidth and low latency and the type of protocols that we're supporting. And MPI has been around for many, many years. Goes back to the Fortran days. So let's take a look at a closer look at Azure. So, and how would you do computation right now on Azure? So for most of you, you probably know that we're doing platform as a service. So the basic architecture is simply a web role. You can have a worker role. So for me to submit a job to Azure right now, and we're not talking about HPC at all here. We're talking about just simply trying to do a workload, heavy workload on Azure. How would you do that? So the way I have done it, specifically for scientific workload, is to use the web role as the front end and use the worker role to do the actual computation. Now we'll go through an example here. So the part here where it says main, this is where you can run your actual executable or any type of .NET computation that you have. So we'll switch back to an example here real quick. So here is a really silly example. All I'm trying to do is to solve the impossible to solve traveling salesman problem. So a traveling salesperson has to go through each of these locations, and you're trying to find the optimal route so that you minimize the amount of travel you have to do in terms of distance. What I have is a web front end, and I'm just simply using the Silverlight Bing map plugin. And on here, I have a few different parameters, and I am using a large instance, which means I have 4 cores running. So right now, they're sitting idle. So for those of you who do real large computational tasks, you want to use large instance or extra large instance. So extra large instance gives you 8 cores. So you guys are familiar with that? Most of you, some of you are. Okay. So for Azure hours, you bill at 12 cents per core hour. So for a small instance, you have 1 core, and you have a medium one. And then you have 2 cores, 4 cores, and 8 cores. So for a physical machine, it maxes out at 8 cores. So I'm actually not running an 8-core instance here. Let's just see what this thing does. So right now, if I hit execute, we're going to start seeing that the CPU really start cranking up. So as many of you who know about scientific computing, it's actually fairly difficult to parallelize your application. Since the traveling salesman problem is embarrassingly parallel, more or less. We're running just simply the genetic algorithm. And I am able to use the Microsoft TPL library, or the task parallel library, to scale out the computation. And it's extremely easy to use. So for those of you who don't know about the Microsoft parallel libraries, it's if you can go on MSDN and look for the parallel computing web page, and it will list all the different parallel technologies you may have. So for this, I'm simply adding them as tasks and running them. So this is one way for you to be able to do heavy computational workload. So I am actually still optimizing this as it goes. So the genetic algorithm is essentially doing generations of your actual computation. You're swapping with your parents, with the child, to see which one is more optimal, and you accept that, and then you repeat that process. So that is how you would be able to do computational work on a large instance or a even a smaller instance. So what if I needed more than one machine? What happens? So you would actually have to write that plumbing yourself. So you would have to take care of communication between the nodes that do the work. And you have to take care of scheduling the tasks. So if you have more than one set of tasks that you want to farm out to many nodes that you want to work on, well, that becomes a bit of a problem, because most of you are scientists. You're not, we're not going to ask you to write that scheduling or load balancer. Instead, we created the HPC product that allows you to submit your jobs through the job scheduler and farm out things for you. So we'll take a look at that. So let me close that. And by the way, all these source codes are available on, well, soon to be made available, and you're very welcome to use that. So let me close that. And the second demo I want to show you is something called the Open Foam. What it is, it's a computational fluid dynamics code. And we are still talking about these demos before SP1. We're not talking about the hybrid solution for SP1. This is simply saying how I did things before there was the availability of that particular product where you can burst onto Azure. So here you're seeing that I have a little selector for this particular app. One is shared memory, and the other one is cluster, and the other one is cloud. So for shared memory, we're simply doing OpenMP or MPI running on a local node. And for cluster, we're actually talking about the InfiniBand hardware that we're taking advantage of. So let me actually show you a demo of that right now. So the cluster here is actually sitting right next to us. It's in a data center out there. So I'm remote desktop into that. Give me 1 second. So when you log on to a new machine here, you simply use the remote desktop. And this little Cray cluster has 8 blades, and each of them have 8 cores, or 2 processors. So that gives us a total of 64 cores. So here's the machine. So let's look at the management console. Can everyone see this fairly well, or do I need to do the zoom in? Okay, we can try that. Was it control space?
Windows.
Control plus? Okay. Windows plus, okay. Ah, there you go. Hey, that is cool. No, I have used it before. Just don't quite remember. So, and also trying to keep you guys awake. So if you look at these nodes, they have, they are, currently doing something, but they're not that busy. So Cray 01 through 08, these are the actual physical nodes that's sitting on my cluster. So they are connected using the InfiniBand hardware. And this thing is not cheap. Every time you're talking about HPC hardware, it's fragile and it's not cheap. So approximately for, in fact, I got a question yesterday. So how much does a HPC cluster cost? So in the ballpark, you're looking at about $5,000 per node if you want to equip it with really good hardware. So if you have, let's just say, hypothetically, we have, I don't know, $400,000. So you can buy in the orders about 200 nodes or so. Am I doing my math correctly? Maybe not. OK, well, you get the idea. So you're essentially doing about 5,000 per node with the best hardware that's available. And it's always 5,000 per node. So let me actually start submitting the job to the cluster. Now I need to get out of it. There we go. OK. Cadium. Cadium is a open source or OpenFOAM is an open source CFD simulation code. And it's actually very popular. So what I'm going to show you is to a little Formula One race car that we're going to run through the CFD simulation. So what we're actually calculating here is the lift and the drag on the actual vehicle, which is going to show up here real quick. There's my little car here, and I'm computing. As it's moving at 40 kilometers per hour, what are the forces of the air acting on this vehicle? So for Formula One race car teams, they probably would want to use much larger clusters than what I have. So I'm going to submit that job and show you how a basic MPI application actually works. So I'm going to submit that job, and what's going to show up on the job scheduler is nothing yet. Anybody know why? It's still writing I/O. So that's the reason. And what we can do is we can actually go to Node Manager, and you can see that the node that I'm currently logged in, it's doing pre-processing. So it has to pre-process the data before it submits to the cluster to run. And let's see, is that actually going well? Soon, we're going to see a job that's going to show up. Ah, there it is. So this is actually not even the real job yet either. So what this part is doing is actually partitioning your data onto 40 different cores that I'm submitting it for. So this job is going to use 40 cores concurrently to do the computation. And here is it actually working. So you can see that it's partitioning the data into 40 different cores. So it may not be very exciting for most people who are not doing HPC or scientific computing, but it's actually very exciting for me because whenever I see this being partitioned, I know my cluster is actually working hard. There you go. Okay, so it's partitioning it onto 40 different cores. So we have a question.
Once you're done with your sentence, could you give us an idea of just what it's trying to tackle mathematically? Why is it partitioning to 40 cores, and how is it partitioning to those 40 cores?
Okay, good question. So the question is, why is it partitioning to 40 cores, and what is it partitioning? So what it is actually doing underneath, it's calling a set of linear solvers. So this is a finite volume code. So for CFD, you have finite difference, finite volume, and finite element. So finite volume is still, there's a lot more people starting to do more finite element code. But finite volume is still the most efficient in terms of being able to converge to a solution. So we're starting the actual run right now. So it's for each of these steps, it's doing multiple linear solves. So these linear solvers are able to actually partition, be able to run it in parallel. So there's just people that have been working on this for 30 or 40 years that has written linear solvers that are based on MPI. So you're essentially solving this giant matrix, and you're passing information back and forth between these nodes. Does that make sense? OK, so that's your linear algebra lesson of the day. So as you can see, there is convergence, meaning that we're actually getting to a solution for this particular problem. Sometimes it doesn't converge. It could blow up, and you say, numerically, this doesn't make any sense. It could happen. And we're using floats only for now. The reason you use floats is because you take less memory. And as many of you are actually starting to use GPUs to do your computation, you would understand that doubles are almost impossible to do in GPUs because they're not available. The newest card Fermi, they only have a small unit that does double for you, right? So most of it, all the cores available on GPU are actually doing floats, right? So floats.
I thought it was doing integer processing. You can do integer approximations.
Yes, that's right. You can do that as well. So it's running, and we can go back and see what are we expecting to see here? They're running at 90% utilization for each of these nodes. What that means is that because of the fact we have InfiniBand, it's able to communicate extremely fast. So therefore, able to utilize all the actual cores available for the system. So what if I had much lower bandwidth? What do you guys expect to see here?
You just use a few cores.
Yeah, that's right. Lower CPU utilization. So it will be running at 50% because the bottleneck is going to be your InfiniBand. So let's stop and think about this for a moment. HPC is really about hardware. What type of hardware you have, and how do you actually be able to do work depending on the type of hardware you have. So Azure hardware, we have 8 cores on each of these nodes. So that is the same. But what are the interconnects? The interconnects are GigE. So there's a big difference here. Fast, high bandwidth, low latency connector, and commodity connectors. So does that mean you can't do CFD on that? The answer is no. And I can tell you pretty much out of the back that I've already tested some of that, which is that you are able to scale to a number of nodes, but not beyond that. So for OpenFOAM in particular, I have tested it to scale up to about 64 cores, meaning 8 nodes. So that is actually quite good for solving a reasonable amount of computation. So if you're talking about weather simulations, a much larger type of computation that requires thousands and thousands of processors, it may or may not scale on Azure. But for smaller type of problems, you're just going to be fine. And Azure, of course, is going to scale very well for embarrassingly parallel, which means there's very little communication required. Each of these cores are cranking away on one unit of a problem independently. So that's the difference. Yes, question?
What if one of the cores gets down?
If one of these cores is dead, let's actually try that. What happens? I am going to take this node offline. Well, the computation continues to go. But if I actually kill it, actually go over and power it off, the whole thing dies because it's one process, right? So that is another problem about reliability. So MPI applications are extremely fragile. So one process dies, you're done. But think about how easily that could happen, right? So if one of them started to, got a divide by zero error, what happens? It's done. So I have to go back and take my node back online. It's in transition. Anyway, so that is MPI. So I did my demo on MPI. And so let's actually do a cloud demo here real quick. So here's Kadium again. So how would I be able to do this workload just simply to Azure without HPC? How would you do that? Well, we'll go back to the same model that we had before, which is the web role and the worker role. So I take my input file, zip it up, send it to the worker role. The worker role takes it and give it to the, send it to web role, and the worker role takes the work, computes it, sends it back to the web role, and web role downloads it back down to my client. So this is how this architecture works. So this is life without HPC first. So let me actually show you how that works. I'm going to open this little computation here. And this computation is going to happen on Azure. Let's look at the preference. So the preference here is real simple. Instead of sending it to the cluster, I can send it to the cloud. And for the cloud, I need two things. One is when I'm communicating to the web role, I'm going to need a username and password. That's the minimum, because you don't want everybody submitting jobs to your little cluster here. Not cluster. So once I'm done here, I can just simply submit this. And it will run on Azure. And once it's done, it will pull it down. And that's right. So I actually had this turned off. But what you saw was the solution. We're doing it backwards here. What you saw was the actual solution. What you see initially is this problem, which it doesn't have the solution in there. So that's how it works if I want to do this without Azure. In fact, I can play a little video for you. Tech writing. Yep. So you can see this is actually how, if I do it manually instead of submitting it from the client. So I simply do that and, take your thing and zip it and send it. And it runs. For simple things, you can do that. And I'll actually provide you with the code if needed. So you can see that I'm actually running this gigantic CFD solution on one of the worker node. So you can see that OpenFOAM is actually running right now. And once it's done, I can just double click on it and I get all my variables up. So there's all my variables that I got, and I can plot it in my client. So this is how it works without SP1. Okay, so now let's actually talk about that. So now, what we just described in terms of HPC is that we have a desktop user that submits a job through the HPC head node, and then you can do your computation behind the back. That's the OpenFOAM demo on the cluster part. And for Azure, you're essentially out of luck. You have to work directly with Azure. You have to write your web client. You have to write your worker role that knows how to communicate with the web role. So for the new product, we added another piece in here, which allows you to control any number of nodes on Azure right there from the HPC cluster. So this is called the Azure burst scenario. When you have extra work that your local nodes cannot handle, it gets sent to the Windows Azure solution. Does that make any sense? And I'm going to show a demo right now. Oh, by the way, here's a little cool animation that we're about to make. So this is a card that actually ran inside the CFD simulation. And I took each of these frames and made them into a RenderMan format. And then I took these frames and sent it to Azure for them to be rendered into a movie. So you have these RIB files, which is structures of the actual 3D frame with the engineering, the mesh. And then once I take that mesh and render it using a ray tracing software for each of these frames, and it gets that part of it is done on Azure. So there's your little nice little race car running through the air, showing you how how the air kind of just disperses around it. Okay, so that's our goal. That's what we're going to do today for the next piece. All right, so if I look at the HPC cluster and I go to node management, you can see all these nodes that are currently online. A lot of these are actually Azure nodes right there. And the way you add Azure nodes is extremely simple. You just go to right-click and say, I want to add a node to my cluster, and Windows Azure nodes, and select the type of instances you want. It could be extra large, large, or small. And you can select 20 or 30, however many you have in your subscription. So if you want to do more than that, so some of you are doing an extremely large computation, you have to have multiple subscriptions. I think each of them support up to 350 cores. So if you're doing thousands and thousands of cores, you're going to need 2 or more subscriptions to be added for your HPC head node. So I'm going to run something really simple here. Instead of adding nodes, I'm going to go to my job arrangement and add a job that we're going to actually run here. Once again, it's on the wrong machine here. I have too many machines running here. So it's the same one. By the way, the HPC Administration Console can be run from anywhere on your laptop or on any of the cluster nodes, so that you have a multiple views for the same data that you're seeing on the cluster. So we're going to submit a job to run. You simply go to New Job from XML, and I'm going to run Aquis. So Aquis is an open source rendering software. You can get that off the internet. So what we're simply trying to do is to take the RIB files that we produced, or the RenderMan input files we produced, and try to make a movie on Azure entirely. So what is the first problem we run into? Getting the data onto Azure. So how would you get your data onto Azure? So how many of you have already tried that? Did you have to write a program for doing that?
Just use your Azure Storage Explorer.
Exactly. So we can use Azure Explorer Storage. And I have one running here, right here on my desktop. So that is called, I'm using Cloudberry storage if you want to use that. So it's actually very simple to use. So the way it works is that you need your Azure Blob Storage account. So for me, I'm just using HPC. I'm not too creative here. So you're going to need your account name, and you're going to need your secret key, your shared key. So how do I get that key, you would ask? Well, that's pretty easy. So you go to your Azure portal. You go to your Azure portal. So if you go to storage down here, where's storage? Hold on one second. Storage account. So there's a bunch of people that have the storage account. So if you right-click on me, which is Wenming, I can actually view it right there. And in fact, I'm going to show it to you. So here's my key. And of course, it's just showing the ... for security reasons. So if you copy that onto the clipboard and paste it into the Cloudberry thing right there, you have access to your blob storage. And I pre-uploaded all my files just by simply dragging and dropping all your files onto Azure. So each of these frames are about 3 megabytes compressed. But if you uncompress it, they're about 12 megabytes. So if you want to send something to Azure, there's a couple of things you can do to optimize that process. One is you want to definitely compress your files. because your internet connection is usually not as big as you usually think. I think my Comcast can upload at about 300 kilobytes per second. And here we can do maybe a megabyte per second. So have you guys tried to actually upload files onto Blob? So how fast was your connection? I'm sorry, what? Gigabytes? But how fast was it? That's the question. You haven't checked it? So usually between 100 kilobytes to maybe a megabyte. So that means it's slow compared to we're actually on blob storage. When you have Ethernet, you can transfer at 100 megabytes per second. So you want to compress your data. You definitely do. So for me, each of these frames is about 25 megs. If I were to transfer the whole thing, which is 400 frames, that's 10 gigabytes. That's a lot of data. So you wouldn't want to do that. So I compressed it down to maybe 1 gig, maybe 2 gigs. So this is how I transferred all my files. Simply drag and drop. Very easy. So now let's do the actual work. So I need to go back to Cray03. OK, so this is a job that I'm actually submitting. So let's look at what this task looks like. It's really easy. So for each of these frames that you're rendering, I'm calling this run.command. And the job scheduler will take care of everything for you if you put a star there. So it will just simply take care of things for you. Once you type that command, it will tell you what it will do. So for 400 frames, each of these frames will run at frame 0, run the run command on each of these. So now you think about what you actually have to really do. The first thing you would do is, actually let's submit the job and see how it's in action first. Let's open that up. So the first thing you do is to copy your actual frame onto the node that you're working on, onto their local disk. And the second thing you do is to uncompress your frame. And then you can render it and then copy it back to the blob storage. The reason is because the blob storage is the part that is actually going to be persistent for you. So if your node goes away, you don't want to keep your files on that node. Does that make sense? Any questions? No? OK, good. So let's actually see it in action now. So I want to go back to the cluster and go to node management and look at the actual heat map on 20 nodes. They are starting to spin up, as you can see. So as you can see, they're starting to spin up. If I go to my job manager, say 11% already finished, and I have 120 of these cores running, which means they are extra large instances, 15 large instances. So I have this cranking away. So if I were to do that whole job on my laptop, it will take me 15 hours, I believe. So here, we're almost finishing up the job as I'm just simply talking to you. So you see how fast that can go? That is the power of Azure. When you have embarrassingly parallel type of applications, it can really scale. So let's actually go back to the node management. You can see that all the nodes are spinning at 90%, 80% utilization. That means we're scaling really, really well. So any questions so far about how this is done? Yeah, go ahead.
You're saying you're storing the actual execution files in the blob storage, not on the node compute files.
That is correct. The reason is because I want them to be persistent. So if I take, so the blob storage is where you're supposed to keep all your files. And then you can spin up nodes to do the computation. But once the nodes go away, if I delete the nodes, you don't know which machine in a data center actually, that machine's hard drive is holding your data. You don't know which it is, right? So if you turn it off, that data is gone. You don't have that anymore. So before you turn it off, you have to write it back to the blob storage. So that's where you keep it. You know it's not going to get lost.
It's not the one web roll.
No, it's not.
Put on the web roll.
No, this is all worker roles. This is all worker roles. You don't have to install VM roles. You don't have to spin anything. I simply right-click and say I want 20 instances of large, extra large instances, and then 15 minutes later, I could start doing my computation. So it's as easy as that. And then somebody always asks me, especially for people who've been doing HPC for a long time, they'll come back to me and say, okay, so that's wonderful, but what about MPI applications? MPI applications will be supported in the next 6 months or so, actually 3 months. So what we have done is that allows you to be able to run MPI in a worker role. So there's no machines to image. There's no images you have to upload. So we can run MPI type of applications. In fact, I have several running in my Azure instance deployment. So that will scale as much as the hardware can support. And much later, I'm sure hardware will catch up. I'm sure we will have really nice hardware in Azure for technical computing. But for now, we're using the generic Azure hardware, which you will have to deal with, and it will solve a majority of computational problems for most people. And you don't have to wait in the queue. And I can tell you a little story that I have never pulled an all-nighter in college. I just never have. I just never done that. And the only night that I actually ever pulled an all-nighter was because Uncar, which is, I came from CU Boulder. Uncar had a machine that has a queue that is just way too long. And we were students. And it took me about 4 hours to wait in the queue to finish a computation in about 2 minutes. So there is no point of doing that. And Azure will solve that problem for you right there. So that is the SP1 demo. And you can do other fun things. And I want to check the time with Yan. How much time do I have?
You go until 1:30.
I can go to 1:30? OK, I have some other cool demos I can show you. Yes, question. Lots of questions.
Yeah.
OK.
We love Q&As. Who's first?
Yeah, OK. So who's first? Oh, OK, well.
Go ahead.
Oh, she's first, I guess. I don't know. Pick one.
Oh, no.
It's a deadlock. OK.
Thank you. So you said that for generic Azure platform, and also at the beginning you demonstrated the cluster.
Yes.
Are they all have the same connection between the CPUs, like the InfiniBand 20 gig?
Yes,
or
the connector, my Cray box is 8 blades times 8 processors each, 8 cores each. It's really 2 processors. So all of those 8 blades have InfiniBand connected to each other. In fact, I can show it to you if you walk with me to the data center. I'll actually show you later.
I know that this one is, but let's say if we're using Azure from anywhere, it's not just directly accessing your machines here. What are the connections between Azure, the servers behind the scene?
So for the machine connecting to Azure is the internet.
Yeah, that's right.
So Azure itself is Ethernet. 1 gig E. I think it's 1 gig E.
Oh, okay.
For majority of the things, it's actually good enough, even for these type of very demanding HPC applications. It's good enough up to a certain amount of nodes. And the fact that most of people don't have access to the national lab machines. If I walk down the hall, walk down the road, and there's manufacturing people doing optimization for these flaps on large trucks, trying to save 2 cents every mile, every 10 miles or something. So those guys don't actually have access to a really large cluster. So for Azure, it's perfect for what they're trying to do. And I am going to show you a demo of being able to use these design optimizations. So design optimizations is the new deal because of the computational power we have right now. There's a company called Optimal Solutions that allows you to take this geometry of a mesh and simply click a button and be able to generate hundreds of jobs for Azure to run, small jobs for Azure to run. So there are a lot of things you can do. You just have to kind of think about the type of problem you're solving and how you can parallelize it in a way that it doesn't require a lot of communication. Does that make sense?
Yeah, that makes sense. And another question is that when we have access to Azure, you said that the extra large instance is about 8 CPU cores. How about if I need 100 or 200 CPU cores like you are doing?
So that is what this product does for you. So I spun up 15 instances, as you can see here. So I have 15 nodes here running. So
is this also accessible?
Azure.
Is this also accessible to the general research stackhouse?
Absolutely. You can spin up as many as you like, up to 350 per subscription. That's my understanding.
Okay.
Of course, the subscription given to me has 350 cores. I don't know what you guys got from National Science Foundation, but my understanding is that you can have multiple subscription add to it. You can use thousands of nodes if you like. I don't know about hundreds of thousands, but probably thousands seems very reasonable. Our scheduler, what you saw here, it can handle up to 1,000 nodes. So this is what we say we handle, but I think in reality you can do more. But we're usually very conservative about the kind of
That's very good
things we can do. Yeah.
Yeah. Last question is that on the conceptual side, when we talk about cloud computing, a lot of people split or separate them from the high-end computing. But from what we heard from you today is that we could integrate them together, and you can use the cloud Azure as the client to upload the jobs to belonging in the
That's
HPC.
correct.
So what is the strategy with the Microsoft about the cloud computing, high-end computing, and grid computing? How they're going to come together or differentiate from each other?
Okay.
Thank you.
So first of all, I am not going to say anything about grid computing because I have experienced it. So grid computing, from my understanding, is that people volunteer their machines, and there's a specific Red Hat installation or a specific installation you have to do. So that has a few applications, or maybe for your instance you have specific applications. What that means is that somebody has to maintain these nodes, and it's not going to be a commercial entity. It's going to be somebody who is a grad student, or it's running in my lab. Maybe you can use it. I invite you to use it. So for national labs, they do contribute lots of these large machines. And they are stable. I love my friends at all the national lab machines. I still have access to them, so I'm not going to have them remove that from me. But so they keep it running. But it takes, for one, dedicated resources, and for two, the amount of software that's installed. So you, as an individual user, I don't think you can go and install anything. At least one of the nodes that I maintained, on the grid, I don't think I allowed people to install things on it. So this is more about, we provide you with this worker role. You don't have to worry about the operating system. You don't have to worry about the hardware. And you have no idea how much grief it is for me to maintain those three, I won't use any bad words, but 3 clusters that would go on and off. And the hardware is just difficult to maintain. And especially for academia, where are you going to put it? The space is limited. Are you going to put it in your graduate student? Are you going to be able to put 8 blades in your graduate student's office? No. You have to put it somewhere. And your admin is going to dictate what you are going to do. I used to be admin, I know. I used to tell people, you can't do this, and you can't do that. So Azure allows you to simply right-click and spin up something and package your application up there and be able to run. So I think that is extremely powerful. Even though the hardware is not there yet, the concept is incredibly useful, incredibly powerful, in fact. So for me, I do a lot of HPC work. And for most of the time, having 5, 10 nodes is good enough for me. So when I really wanted to run scalability tests, we run it on national lab machines when it comes to thousands and thousands of nodes. Even that, you are going to have to wait in the queue for a long time. So that is the reason why I think that Azure is extremely powerful. The fact that you don't have to worry about the operating system, you don't have to image your operating system, you don't have to worry about the hardware. So that's where, what I was able to convince myself that Azure is useful for HPC. So the roadmap is that, we are going to have better hardware. We are going to have dedicated hardware for this type of computation. But I don't know. If I knew, I would be able to tell you, but I really don't know what our specific roadmap is. But just using common sense, I can simply see that this is where everyone is going. So does that make... Oh, we have more questions over there, I believe.
First of all, is it your claim that the Azure computing solution is meant to be less brittle than the Cray example you showed first? So if you have some nodes drop out during a computation, some hardware crash or whatever, is it your claim that it doesn't follow that single process, single job fragility?
That is yes and no. First of all, the agility and being fragile is more of the application scenario. So, for example, Mpi is extremely fragile. One of the process dies, the whole thing crashes. You're done. It doesn't matter what kind of hardware you run it on. You run it on national lab machines, you run it on your local cluster, you run it on your desktop. It doesn't matter. And if you do this on Azure, it'll crash. There is no magic in that. It's about application scenarios. So what we are running here is simply embarrassingly parallel. I'm running this executable 400 times. I'm not doing anything more complicated than having any kind of dependency between the jobs, right? So this is what I am running. And MPI you would be able to run MPI on these commodity hardware. Does that mean they will be less fragile or more fragile? Well, they are going to be more fragile than my high-end cluster in terms of the actual physical hardware. But the nice thing is that if it dies, you just say, yeah, get another one. So you will be able to do that. But I can't. I got stuck with my cluster, and if it dies, I'm stuck with it. So I can't say, hey, can I swap another one for 10 minutes? It just doesn't happen. So yes, it can be more fragile in terms of the actual hardware, but I haven't seen one crash on me so far. And I wouldn't even know, right? If it does go away, it could be rebooted or something else could happen to it. I don't know. It could be swapped out. But in terms of, from your user's perspective, it doesn't matter. So for me, I just spin up another instance. It doesn't cost me anything. It's Microsoft's problem if the hardware dies. Well, not Microsoft's problem, the guys who's maintaining the data center's problem. So what happens is that they see enough units die, they just take the whole thing and come in with a truck and say, yeah, we're out of here, and just bring in another big block of them. So that's how it works. So think about it. There's no sysadmin maintaining these machines, so it takes the cost down. So that's the reason that Azure actually happens. So I want to actually show you another demo real quick before we go to break.
You want to take a couple more questions?
Yes, I apologize. Yes, I'm sorry. I'm kind of keep ignoring.
I have several questions. First one is, your application is written by C or C++, right?
That's correct. And I can go through how you can migrate an entire Unix application to Windows without much work. So there's some new work being done right here in the data center here. In fact, I sponsor the GNU C++ team for Windows GCC compiler. What that means is that you would simply build your Windows application on Linux machines or whatever you have, and take that binary and be able to run it natively on Windows, and it's not even emulated. So I can show you how to do that. I'll point you guys to the websites, and also the application you saw, OpenFOAM, that was entirely, it's 1 million lines of code. And I tried to do a Visual C++ port. It's still ongoing. I finally got it working. It's a year and a half. And it's just incredibly difficult. But I cross-compiled it on Linux. It's working just fine. That took me 3 days. And so those are the kind of things that we want to provide you to be able to take your research work. And sometimes they are on Linux. Sometimes they're on the another platform. Simply take that and move it onto Windows. And that same binary is going to run on Windows Azure, Windows Client, and also Windows Server, and that's HPC. Because Windows is binary compatible back to DOS days. So that is the advantage of having Windows. Hopefully that answers your question.
Actually, my question is another one, but I have this question for this one too. Okay, so your the middleware, you can add your own nodes, right? The nodes can be both Linux and Windows together.
No, you cannot. Well, maybe VMroll might support that in the future, but I don't think it. So currently, it's worker role. Worker role is Windows. In fact, if you remote log in, it is just simply a Windows machine. So what I meant in terms of being able to run a Linux piece of code is that you actually cross-compile it. It's like, when I'm developing my phone application, it's cross-compiled. The phone processor is an ARM processor. So you compile it for that platform. So once that's done, you're actually receiving a Windows binary. So you take that Windows binary, and then you can run it on Windows Azure or Windows Client. Does that make sense?
Yeah, makes
sense. So
sense.
these tools are actually available on Linux. So we sponsor that, and we make sure these are available so that you can do things very quickly and easily.
Yeah. There are many applications actually written by other language like the weather forecasting usually written by Fortran, right?
That's correct.
Does your system support those language applications?
Absolutely. As long as it's a Windows binary, we support it. In fact, you're talking about Wharf. I have it running on my cluster. I think 2 years ago, I actually live in Boulder, Colorado. So I grew up in Boulder, Colorado. So I know all the guys in NCAR fairly well. So we actually have a Windows port of Wharf, or WRF, the weather research and forecast code. So that currently runs on my cluster. And I was just sitting there, and I was trying to get it to work on Azure as well. And it should work. There's no reason that it wouldn't work. But in terms of scalability, once again, that has to do with the physical hardware. So it may scale, I'm guessing, just from what I was just doing, I'm thinking probably will scale up to about 64 cores for, Wharf.exe. So that might run. In fact, this afternoon I have a demo of running Wharf on GPU, and I don't think anybody in the world has done that, but we are able to speed it up by 500 times just simply using GPU. So, any more questions?
Okay, I think I'll move on.
Benchmarks between Windows and Linux, because we use Azure.
That's a really good question. So the question is, is Windows faster or slower in terms of performance? So there are many factors about performance. There's something called lies, damn lies, and benchmarks, right? So a lot of these applications are initially targeted for Linux. There is no reason for them to work just out of the box to perform exactly the same. But at the same time, hardware is hardware. Intel hardware is Intel hardware. So in theory, they should work just fine. So I have seen applications that have been ported that works identical benchmarks. And then I have seen applications runs 50 times slower out of the box. But by tweaking a little bit in terms of I/O or something that you may have done wrong, or maybe one specific system calls is different from Windows to Linux, by changing some of that, you can fairly quickly figure out how to make it within 5 to 10%. And also there's dependencies of compilers. So you have compilers that, Intel compilers may, compile certain things faster on Linux, certain things slower on Linux. So those are some of the factors that we cannot actually control. But most of the time, it should be within 5%, meaning that Windows could be faster by 5%. Linux could be faster by 5%. And in the case of Fluent, we ran the benchmark. I think Windows was faster. In the case of codes like PAM crash, LS Dyna type of code, it's comparable. In terms of OpenFOAM that I did the cross-compiling in, it's 10% slower, and I'm still trying to figure it out. And I know it's not I/O, so there's something else going on. So, it just takes time to figure it out because a lot of these codes are millions of lines of codes, and I have been through some of them. But usually, with a real company, even for Linux companies, you have a room full of people doing optimization. So here we're a small group, so we don't have that kind of resources. So what I do is when I have time, I'll look at it. But otherwise, It may be a little slower. For end users, it does not matter, whether it's 5% or 10% slower. If it gets the job done, that's what counts. So that's 12 minutes left. Hopefully that answers your questions.
Yeah, thank you.
Great. So here is a little problem that I want to show you. So there's a company called Optimal Solutions. You can go on, look it up on the web. So these guys, what they do is they take your geometry, your CAD, your pre-mesh. They take that mesh and be able to generate hundreds and thousands of CFD run with slightly different parameters. So what it does is it simply does what is it called? Latin hypercube. So for those of you who are familiar with that concept, so the simplest concept is called Latin square. What that means is you're trying to take a m by m matrix and take n numbers of letters and try to kind of distribute that in that square. So Latin hypercube is more dimensions. So here, what we're trying to do is selecting a few variables and say, I want to automatically generate a set of runs that with slightly varying parameters. So we're simply doing design optimization, trying to figure out which one is the best configuration. So it's based on statistics. So what happened was 60 human beings was able to get it, this few injection thing, 0.6% improvement. And the computers took maybe 2 days. By running, hundreds and hundreds of cases, was able to get 3%. And, think about how much money we're saving GM over, and also the consumers that are running these cars. So this is the type of problems that Azure can help small businesses to be able to scale. So before doing this company bought laptops. And I asked them, why did you buy laptops? They said, oh, well, we can sell it on eBay once we're done. But hey, now you can do it at 12 cents per core. So instead of going out to eBay and buy laptops and sell it back, you can do this. It's much more scalable and a lot less work. So that is all I have to say about SP1. And there are more resources you can find here, and all the links that that's in this slide. I'll make sure that this slide is available to Yan. So for the afternoon session, what I will do is I would actually go through some of the community work that I'm doing in terms of how you can make your job easier in terms of building software, working on visualization. So we have parallel visualization, we have GPU, we have a lot of exciting things that we can show. So that's my session. Any more questions?
Do you have a workflow on top of this?
Do I have a workflow on top of on HPC itself? No. The answer is no. But you can actually create your own SharePoint or other types of UI to do that. So one of the things that Microsoft Research has is something called Trident. So they've actually integrated HPC with this. With Trident framework, you can actually simply do the automation using the Trident framework if you want to. And Dean is right there. He would be able to answer that much better than I can.
Right. We got Dean back here.
That's right.
It's just specific for Trident questions. So if you have that, do grab him. I want to give them 5 minutes to relax a little bit before Julia starts.
And I will get my lunch. All right. Thank you.
I appreciate it so much. Thank you.
You're very welcome.